Welcome back. I'm going to talk a little bit about this decision that we have to make on discrete versus continuous as far as time and populations. So let's start with discrete versus continuous time. When you're building this model, this disease model, you have to decide if you're going to treat time as a continuous thing, meaning that, say, your recovery time could be 1.35 days, or it could be 12.72 days, or any value of time. So you can get into partial days, you can get into minutes, seconds. It doesn't actually break into chunks. It's any time you want. Whereas discrete time is this distribution on the right where we've made a histogram of this continuous distribution. And by making the histogram, we've broken it into chunks that you will recover at 2 days, or at 3 days, or at 12 days. So we're setting it up into chunks of time rather than this continuous time. Now, we know that time is continuous, right? Time does not happen in chunks. Time is naturally continuous. But sometimes it is easier to think of it as these discrete chunks. Now, from the perspective of certain analytical approaches, continuous time is the easiest way to do it. We want to use continuous time because it allows us to use certain mathematical approaches. Discrete time can make your programming easier. So when we set the time step, if we are doing discrete time, we have to decide how we're going to break up this time. Continuous time, obviously, if you have continuous time, you don't have to break it up. You don't make this decision. But if you do have discrete time, you need to decide what that time step is going to be. And the first question you have to ask is, how often do things happen? Because the first rule of discrete time in a disease model is that no one person should have multiple events during your time step. Meaning your time step has to be short enough that a person can't be infected and recover throughout the course of a single time step. If they get infected in that time step, they are still infected at the end of that time step. If they are infected at the beginning, they can recover, but they can't get reinfected. So the time step has to be small enough that it captures only one event per person per time step. And so we look for these natural breaks. And I like to say in the class that I teach that you think about how people describe the outbreak in order to decide what breaks you're going to use when you're building your epi curve. And it's the same decision with your modeling, that you look for these natural breaks in time periods. So for a viral infection with an acute phase that works very quickly, a day is a natural break. You could do a half day, but it's not really as natural. Whereas in other things, you might want to have a week or a month. A year is usually, for an infectious disease model, too long of a break, but you're looking for these natural breaks that occur. And when we're setting the time step, we also want to do some convenience things. So if I want to be able to look at the weekly cycles, then I might set a day time step so I can look at weekdays versus weekends. If I'm doing a longer time period, I might want a 1 week time step or a 1 month time step, because there are certain things that happen on that schedule. So looking at the discrete time steps, think about how often things happen, when natural breaks would occur, and what is convenient for your modeling purposes. Now, discrete versus continuous populations. Here is where it makes more sense to people to have a discrete population. A discrete population says an event can happen to a person, not a part of a person, just an entire person. So think about that image on the left. You've got mom, dad, and a kid. And if a person gets infected, it's one of those people. You won't have half a kid infected. You know, we're not talking about the nuclear family with 2.5 kids. You've got a kid infected or a mom infected. It's not this 0.2 of a person. With a continuous population, you don't force the model to break it into individuals. So you're not forcing integers. You're allowing the population to flow as a continuous variable, that if you have 100 people, 0.1 of a person could get infected. I know that seems weird. And it is weird in a small population. But if you think about a very large population, and you're thinking about the population moving as proportions of a large population, continuous populations make more sense. So if you say I have a population of 1 million and 0.1 of that population moves, that's a lot of people. So you can think about continuous populations more easily in the large sense that you've got as many people as there are grains of sand in an hourglass. So, you know, one, two, three, it's not quite as important to break it up as individual people. There are issues that come up with this with modeling, but in general, if you have a large population, this continuous population is fine. If you have a very small population, it gets a little bit harder to justify and to wrap your head around. So there's discrete versus continuous for time and for populations. You can combine them in different senses. So you can have continuous time and discrete populations. You can have discrete time and continuous populations. You don't have to do all continuous or all discrete, but you have to make that decision. So happy decision, happy model making.